Okay, so let us now look at examples of various types of cooperative games. So the most trivial cooperative game that one can think of is what are known as additive games. So we are going to say that a game, NV, is called additive if the following property holds true. So we have got here the property which says that the coalition function or two disjoint coalitions S and T is going to be such that the V of S union T is always going to be equal to Vs plus Vt, regardless of whichever pair of disjoint coalitions you select, right? So this property has to hold true for any disjoint coalitions that you are selecting. Now, what is the meaning of this in words, right? So basically, this is saying that a game is additive if every pair of disjoint coalitions in it are such that the members of any coalition obtain as a group exactly what they would have obtained had they been acting separately, right? So the significance of this is that this basically tells you that if a game is additive, there's no advantage of forming coalitions because a coalition does not provide anything extra compared to what each member could have obtained on their own, right? So let's just see an example to kind of like make this definition a bit more concrete. So imagine that you have the following situation. So you've got three players called 1, 2, and 3. And we have got the coalition function as follows, right? So as usual, you have got the empty set leading to a value of 0. You have got V1 equal to 5, V2 equal to 10, and V3 equal to 15, right? So these are things, imagine, that are given to you, okay? Now from here, if we know that this is an additive game, we can actually specify all the other values as well, right? So for example, V1, 2 would be V1 plus V2. So that means 5 plus 10, so 15, right? V1, 3 is going to be V1 plus V3. So we have got 5 plus 15, so 20. V2, 3 is equal to 10 plus 15, so 25, right? And V1, 2, 3 is equal to V1 plus V2 plus V3. So that if you add them up, that's 30, but you could have also got it from adding up, let's say, V1, 2 and V3, right? So different ways you could have done it. So this is an example of an additive game, right? So you could have a situation where you're told an additive game and you're given some partial information about the coalition function and you have to fill up the rest. Or you could have just been given information about the different values of the coalition function, and then you could have been asked whether it's additive game or not, right? And recall that the significance of an additive game is that our prediction is going to be that, there's not necessarily we are going to see like, larger and larger coalitions coming up because there's no advantage of forming coalitions in some sense, right? Okay, so let's now look at an example of a game where actually there is incentive for coalitions to be built up, right? So this is a slight variation of something that we just saw before. So we are going to say that a game is super additive if the property that V of S union T is greater than equal to Vs plus Vt holds true for every pair of disjoint coalitions S and T, right? So if you compare it with additive, in additive case, you had equality, but now you are allowing for greater than equality, right? So then that means that you are kind of like having a more structure, right? Okay, so what does that mean in words? So this is basically saying that super additive game is a game in which every pair of disjoint coalitions can obtain jointly at least as much as they could have obtained if they were acting separately, right? So basically this is ruling out situations where if you kind of like combine a larger group consisting of several smaller groups, you're going to get at least as much as you would have got if you just had kept the separate group separately, right? So basically, there's no kind of like negative externality, if you like, of forming a larger group, right, among the group members, right? So one implication of this is that it is actually always advantageous to form bigger coalitions because as you are kind of like increasing the size of the coalition, you are ending up getting higher and higher payoff in total for the coalition, right? So that basically provides incentives to form larger coalitions, right? So basically, then if we were to kind of like predict what would actually happen in terms of the coalition that you might expect to see, then one prediction would be that you might expect to see the coalition consisting of all the players which are playing in this game, right? Because each addition of the player is kind of like increasing the size of the coalition. And then the question then becomes, okay, suppose that all the players have decided to be part of the coalition and it's going to generate a value of V of n. Then the question is, how do you divide this total payoff among the different coalition members, right? So there we would expect, certain properties to hold true. So imagine that we have kind of like decided to split the total value of the coalition among different members in the following way, that we are going to give player 1 x1, we are going to give player 2 x2, and so on. We are going to give player n actually xn, right? And in this case, we will expect that certain properties are going to hold true, right? So what are those properties that we would expect to hold true? So the total value of the coalition, remember, if all the members are part of this coalition, is going to be Vn. So the amount that we are giving to each player, that has to add up to Vn. So that property is basically called group rationality or efficiency, right? So this is suggesting that you would expect the two things, right? One, the grand coalition to be formed, and once this grand coalition, which consists of all the members, is formed, you would expect that this amount is going to be kind of like split off among different players, right? But you would also require a second property, which goes by the name of individual rationality, right? So what this is saying there is that it must be individually kind of like incentive compatible for every player to actually join the coalition. And this can only happen if they're getting a payoff at least as high as the payoff that they were getting if they had just decided to stay on their own, right? So, for example, if one had decided to just stay on their own without joining any coalitions, then one would have got the payoff V1, right? And so what we are saying is that in the final outcome, then the amount that is going to 1 has to exceed the amount that it was going to 1 if one had just decided to stay off by himself or herself, right? And this has to hold true for all the players, right? So x2 has to be more than v2, right? Again, x2 is the amount that is going to player 2 in the final outcome. And v2 is the amount that player 2 would have got if he or she had just decided to break off and just form a coalition of one person, right? Which is player 2, right? And this holds true for all the players, right? So we would expect that these properties necessarily has to hold true. Okay, let's look at an example of a super additive game. Imagine that you are given the information about this 3-player game as follows. These are the characteristic function values that are given to you. Let's verify that this satisfies the definition of super additive game. So we notice that V1 equal to 6, V2 equal to 18, and V3 equal to 12. So V1, 2 is 24, and this is greater than equal to 6 plus 18, right? Which is V1 plus V2, so that is fine. V1, 3 is 20. And again, this is more than basically 12 plus 6, which is V1 plus V3, right? And what about V2, 3, which is 35, which is again more than 18 plus 12, which is equal to V2 plus V3, right? What about V1, 2, 3? So 50 is more than 6 plus 18 plus 12, which is V1 plus V2 plus V3. But you should also verify that it's more than, let's say, V1, 2 plus V3, right? Which is 24 plus 12 and so on, right? So you can verify that this definition that we had listed here, this is actually kind of like satisfied, right? So you have to make sure that all these definitions are checked, right? So that's an example of a super additive game. Okay. This now kind of like being inspired by elections, think about like what sort of coalitions and what are the questions that might come up in this kind of games, and how do we represent them as cooperative games. So oftentimes, you might have like different ways of aggregating preferences, as we discussed, right, in a previous lecture. So this might be the election rules, and they would kind of like often specify which subsets of the voting body are enough to pass a decision and which do not meet this requirement, right? So the subsets that can pass a decision are what are known as winning coalitions, and the coalitions that are not big enough to pass a decision on their own are called losing coalitions, right? So sometimes, we might have an electoral system where it's majority voting, in the sense that if at least half of the members are kind of like willing to vote in favor of one, then their decision is going to be respected, right? But you might also have a more complicated system where just a simple majority might not be enough, right? So, for example, if you might have a requirement that, if you want to change some fundamental rules or constitutional amendments, then you might have a requirement that more than half majority is required, right? So you may have like super majority requirements, or you may have a requirement that at least 2/3 people must agree, and so on, right? So it depends on what type of laws are we talking about, and what are these election voting bodies that we are talking about. Okay. Okay, so the significance of kind of discussing this sort of situation in this kind of lecture is that we can think of the voting body as a coalition function game, right? And so the way to do it is to assign a value of 1 to every winning coalition and a value of 0 to every losing coalition. Now, in contrast to the examples that we have seen before, this 1 and 0 does not refer to the monetary value of the coalition, right? So the value 1 kind of like indicates the ability to pass decisions, right? So if we are saying that a coalition has a value 1, it means that that coalition is a winning coalition, right? And therefore it can pass a decision. So 1 signifies that, and kind of like the number 0 would indicate that that coalition is not enough to kind of like get a decision approved, right? So that would be an example of a losing coalition. Okay, so let's take a look at a simple example to make sure that we have kind of like understood this concept. So imagine that you have a 3-player majority game. And basically this game consists of a committee which has 3 members. Okay, and to pass a decision, right, to approve a decision, agreement of 2 members is sufficient, right? However, if you have only 1 member in favor of the decision, this is a minority, and then therefore the decision is not passed, right? So how would we kind of represent this as a cooperative game, this situation? So again, 3 players, right? N is 1, 2, 3. Each of the members on their own are kind of like not enough to pass this rule or this bill, let us say. So in that case, we have that V1 or V2 or V3 individually are equal to 0. However, 2 of them are enough, right? So that means if 1 and 2 have come to an agreement and they want to pass the bill, they can do it. So therefore, V1 2 equal to 1. Similarly, V1 3 and V2 3 are also going to be equal to 1, right? And if 2 members are sufficient, then 3 members will, of course, always be able to pass. And so therefore, V1 to 3 is equal to 1. And as before, V5 is equal to 0, right? So that's an example of a simple 3-player majority game. Okay. So what kind of questions can one ask? So this is just to anticipate what we might see in future kind of like segments or lectures. So one question to ask in this type of situation is that what is our prediction about the coalition that we expect to be formed, right? And how likely are the members of this coalition that is going to be formed? How likely are to kind of like, what share would they kind of want to do, right? So from here, intuitively, we can kind of like reason the following, right? So if coalition 1, 2 is formed, they get the decision approved, right? And then perhaps, this 1 that they have kind of generated, they may want to kind of equally split it among themselves, right? So therefore, player 1 ends up getting 0.5, player 2 ends up getting 0.5, and player 3 ends up getting 0 perhaps, right? Out of the total value that is generated, right? So they are basically equally splitting it off. Similarly, if coalition 1 and 3 is formed, then the outcome is likely that 1 and 3 get to split it off the total value equally, whereas 2 ends up getting nothing because it's not part of the winning coalition. And similarly, if the coalition 2, 3 is formed, then the outcome is likely to be 2 and 3 getting to equally split the value of the coalition, whereas 1 gets nothing, right? But however, you could have also kind of like maybe approached a judge and asked the judge to propose a fair distribution, right? So here, probably one thing that might be an important part of the reasoning is to kind of like think that, okay, there's nothing special about 1 or 2, right? So why should like 1 or 2 necessarily get to form a coalition, right? And similarly, there's nothing special about 2 or 3 or 3 or 1, right? So there's no reason to per se leave out anybody, right? From the judge's perspective, right? And the judge might reason that, if you have like all the 3 players coming in, it's not also going to reduce the value of the coalition, right? So you might as well go with all 3 players. And because of the symmetry of these 3 different players, perhaps the best option is to actually assign them a value of 1/3 each, right? So this might be one of the outcomes that the judge might propose, especially if fairness is a consideration. Okay. All right. Let's look at the example of a majority game, but modified slightly. So this is what is known as a weighted majority game, right? And imagine that there's a city with like 3 parties in the assembly, and the following parties have like different strengths, right? So party 1 has like 5 members in this assembly, party 2 has 3 members, and party 3 has 7 members. So these are the only members. So basically, you can see that it consists of 15 members, right? So here the weighted word comes from the fact that we are basically assigning a weight to each of these parties, right? So then therefore you have got Wi representing the weight of party I. And in the above example, we will say that W1 is equal to 5 because party 1 has 5 members, W2 equal to 3 because party 2 has 3 members, and W3 equal to 7 because party 3 has 7 members, right? Okay. Why is this kind of like a useful way of thinking? Because in a lot of like elections, you might have like rules which specify that you have to vote according to your party line, right? You cannot go against what your party wants to vote on a particular issue and vote for um, another kind of like decision, right? Maybe opposed to what the party wants, right? So basically, if you like, there's no cross voting which is allowed, right? So how would we describe a weighted majority game? So it has like two parts, right? One, you have to specify what is called the quota of the game, right? We are going to denote that by Q. And it is also specifying what are the weights of the different agents that are out there, right? So it's a cooperative game, right? So we can think in terms of our usual notation of N and V. So the requirement is that each of these weights have to be taking a non-negative value, right? So W1 is greater than or equal to 0, W2 is greater than or equal to 0, and so on. And the value of the whole coalition is going to be equal to 1 if the sum of the weights of this coalition S is greater than or equal to Q, right? So that's the significance of the Q here, right? So this is telling us that you require a size of at least Q of the members that are in the coalition in order to kind of like get something approved. And if this is not reached, then VS is equal to 0, right? So again, this number Q is called the quota of the game. And that refers to basically the number of weights a coalition must command in order to pass a decision, right? So we'll see examples soon, but I just want to highlight that there's a particularly interesting subset of this class of games that we have been discussing, which is known as a strong weighted majority games, right? So this is basically a game where the quota is greater than half of the sum of all the weights. And the strong weighted majority games actually satisfy the following property, right? So it has this property that an empty coalition is a losing coalition, right? And a coalition of all players is going to be a winning coalition. So that is kind of like fine. But then we have also this interesting requirements, which says that if you have got S is a winning coalition, then the coalition of players not in S has to be a losing coalition. Whereas if S is a losing coalition, then the coalition of players not in S has to be a winning coalition, right? So let's take a look at an example. So imagine that you have a game. Remember that weighted majority games are described in this format where you specify the quota first and then the different weights of the different entities. So this is the Q equal to 9 and then W1 equal to 1, W2 equal to 7 and W3 equal to 9, right? So what this means is that in order for the decision to be passed, you need at least 9 members kind of like voting in as a coalition, right? Okay. So is 1 going to be enough here? Party 1? No, because it has got only 1 member and you require 9 members in order to pass the decision. So therefore, you have got V1 equal to 0. So V1 is a losing coalition, right? Similarly, party 2 has like 7 members and that's not more than 9. So again, this cannot actually make this decision, but V3 is equal to 9, right? And then therefore it has this 9 members that are required to pass a decision. And so therefore V3 equal to 1, right? What about 1 and 2 forming a coalition? So then that has 8 members. But again, this is not more than 9. And so therefore V1 2 equal to 0, right? What about 1 and 3 getting together? So 10 members, which is more than 9 members required to pass the, let's say, the legislation. And therefore V1 3 equal to 1. And similarly, V2 3 is also going to be equal to 1, right? Because 2 and 3 getting together means that they have got now 16 members, which is definitely greater than 9. And so therefore they can pass the decision if they get together, right? And of course, all the players together here. So that will be 17 members. That is again more than this 9, right? So you have this property. Now, let's make sure that they also satisfy these properties that we listed of this strong weighted majority game. So this says that property 1 says an empty coalition is a losing coalition. So clearly we can see from here that empty coalition is not going to be enough, right? A coalition of all the players is a winning coalition. So if you have got all the players 1, 2, and 3 kind of like getting together, that will lead to the decision being passed, right? It says that if S is a winning coalition, then the coalition of players not in S has to be a losing coalition, right? So let's verify that. So we can see that 1 to 3 is a winning coalition. The set of players who are not there is 5, so that is a losing coalition from here. 2 and 3 is a winning coalition, right? So therefore, that must imply that 1 is a losing coalition, which is verified. 1 and 3 is also a winning coalition, so that must imply that 2 is a losing coalition. But 1 and 2 is a losing coalition, so that must imply that 3 is a winning coalition, which is true here, right? And similarly, V3 is a winning coalition. So, 3 is a winning coalition. So 1 and 2 is a losing coalition. Again, that is satisfied. 2 is a losing coalition. So that means 1 and 3 has to be a winning coalition, satisfied. And again, 1 is a losing coalition. So therefore, we require 2 and 3 to be a winning coalition, right? So you can kind of like see from here that all these properties are satisfied. So another interesting thing to note in this game is that you have this interesting property where basically whichever way 3 is kind of like going with, that decision is going to be passed, right? So from here, you see that 3 alone is enough to pass the decision. And if 1 and 3 get together, that's also going to be enough, right? Because definitely now you have more members. And similarly, V2, 3 is also going to be equal to 1. And V1 to 3 is equal to 1, right? But if 3 is not in favor of passing the decision, then the other players cannot get together and get the decision approved, right? So this would be an example of a kind of like a dictator in the sense that we have been talking about in previous classes as well, right? So here player 3 is a dictator because her consent is basically necessary and sufficient to pass any decision, right? Okay, let's look at one final example of this sort of like majority games. So as I mentioned, sometimes the required majority is not just a simple majority in the sense that you require a greater than equal to half the amount to be passed, but a decisive majority, right? So this would be an example where suppose you require 2/3 majority to pass a decision, right? So let's look at an example there. So again, you've got 3 players and the weights of these 3 different entities are given by 50, 40, and 30, right? So if you add up, then you see that the total weights is 120, and 2/3 of 120 means that a weight of 80 is required to pass a decision, right? So would 1 be enough on its own? No, because 50 is less than 80. Would 2 be enough on its own? No, because 40 is less than 80, and also 3 is not going to be enough, right? What happens if 1 and 2 get together? Then you have got 90, which is more than 80. And so therefore 1 and 2, if they get together and form a coalition, that's enough to be a winning coalition, right? And similarly, 1 and 3, that is also 50 plus 30, 80, which is greater than equal to 2 by 3 of 120. So that's again enough. But if you have got only 2 and 3 coming together, so that's total of 70, which is less than 80, which is the 2/3 that is required, right? So B of 2, 3 is 0, right? So finally, we also get our usual kind of like result that all 3 are going to be enough, because definitely that means that everybody is in favor of the decision. And we also get this result that the empty coalition, of course, is not going to be enough to kind of like pass this. And so it's always going to be a losing coalition, right? So this kind of like is something that you can kind of extend to just thinking about not just about simple majority, but, majority with like different requirements that would be needed to pass a decision.